in sort of themes, one way to think about it, and there's various ways to slice and dice our portfolio. But we have applications in energy space, material science, economic competitiveness or economy, earth systems, scientific discovery, healthcare, and biology. So this application portfolio was selected very carefully over kind of a 6-month process in negotiating with our DOE sponsor which applications are sort of most important strategically for the DOE mission. And so it wasn't just about applications that are petascale ready, that have the best performance now. It's a mix of applications, some very immature, some very petascale mature, and so we have a mix of risks with regard to performance. But basically, the requirements driver for ECP is to deliver applications for DOE mission needs. So it's quite an eclectic mix, I think you'll see. So I'm now going to take you through some. I'm going to go very quick, and I apologize, but I have a lot I want to say, and so I'm going to talk fast here. So in energy security space, so we have a turbine wind plant application, we have a small modular reactor application, and we have a subsurface application. I'm going to say a little bit about each application. So with you see in blue kind of the impact. In other words, we believe if these applications can address the challenge problems that they're targeting, that they'll have real impact. And I'll use the wind plant as an example. Today we can do turbine resolve, kind of single turbine resolve simulations and understand turbulence shedding and sort of fluid structure interactions with one turbine. But we can't do that for whole wind plants, say turbine plants of 50 turbines, say 50 to 100 megawatts over 100 kilometers squared. We don't understand the interactions from turbine to turbine. And in fact, studies have shown that you can lose 20 to 30% of potential wind energy just from the turbine-to-turbine interactions. So we need to simulate an entire wind plant. And to do that's definitely an exascale problem. And ultimately this will lead to better designs, but even more downstream, potentially sort of smart automated operation of the turbines, being able to say with machine learning, being able to understand the conditions in the local atmosphere and adjust accordingly. This is a CFD application, it's a structure application, and also a weather application because you have atmospheric boundary layers. So a typical theme of these applications is you've got multiple kind of single physics codes coming together and interacting potentially for the first time. And so for our application development effort, we're driving a lot of very new capability, and we kind of put our applications in two classes. A new capability that really doesn't exist in our space at all, or an existing capability that is going to go hard after performance to really pursue better resolution or better science. So we kind of have a mix, and this is an example of really a new capability. Small modular reactors. Here we're talking about full core Monte Carlo coupled to CFD, so stochastic method with the continuum method. And assuming you have your cross-sections right for neutron transport, you pretty much get a gold standard answer, almost as good as experimental data if you have enough particles. And here we're talking 50 to 100 trillion particles for a full reactor. Obviously, a virtual test reactor to sleuth out designs and being able to decrease that design time cycle is very important. Subsurface really impacts CO2 sequestration, petroleum extraction, geothermal energy, or nuclear waste isolation. So here you're talking reservoir simulations on the order of a century with potentially hundreds or thousands of well bores. So you've got to understand thermomechanic cracking. You have to understand reactive advective flow, porous media. So again, two sort of complicated codes coming together. This one really points to a number of Department of Energy program offices. Clean fossil fuel combustion. This is an interesting application where you have chemical looping reactors and basically fluidized beds talking back and forth, burning coal cleanly, biocatalyst design. So here basically next generation electronic structure and chemistry is very important for us. I know Yutong is up here, so I'll hit a few applications. Materials for extreme environments, so accelerated time scales for molecular dynamics, higher accuracy length scales, time scales. This is a very important application for a lot of fundamental material science. We're going after additive manufacturing. We're going to simulate 3D laser and e-beam printing. It turns out for metal alloys, it's not uncommon at all to have rejection of parts that are for high spec parts that are printed for metal alloys. Quantum chemistry. Really, this could be a game changer with regard to high-performance electronics, sensing, and storage. In this case, quantum Monte Carlo, the goal is 1,000 atoms. That doesn't sound like a lot, but today we're doing 20 to 40 atoms. And so 1,000 atoms, 10 to 15,000 electrons, being able to do metal oxides that are getting sizable enough where we can actually think about designing. We have a power grid application, and I promise I'll go quick here, Yutong. Smart city application, earthquake hazard risk assessment, gas turbine design and combustion engine design. So these are sort of traditional and some non-traditional in the case of power grid. An Earth system climate model, more chemistry, and metagenomics. This is a newer area, so genome assembly, very important for bioremediation and microbiome. Here we're doing genome assembly and protein clustering. Standard model particle physics, so this is cosmology. We have a QCD application, and